let me talk about something else because it's fun. So basically, the motivation for my research throughout the years is to keep finding evidence for again inflation. So first, let's do that. So support the evidence for quantum fluctuation. If there are three quantum fluctuations in radian, the fluctuation should rank out from 6 to 100%. If it's that, so that's the count of number of pixels having some value of fluctuation. The function is fluctuation at the Gaussian distribution. You look at the data. That's what I have. And so you basically say so you basically say this is one distribution in essence. You think a function generally take this to the multiplied by 10 mathematics and integrate and should be zero to the function. So you can do this. You look at three different locations in space. So multiply these three different values together and you average over the whole sky. Observe the density between and as a result, we show that we value that optical direction from Gaussian to less than whole string per second. Incidentally, we parameterize this general continuous parameterization. So you'll get the sum of linear delta and delta square. So this totally square part temperature is no longer about. And you try to use it for picture here. This is a linear final result with that seems big, but you realize that the data here is exactly about 5. It's about 5. That's why up or down is 45 for system. And front, you can find that there's no other either, and it improves up or down by 5%. So it's a remarkable speed of Gaussian. In fact, only the other side. How about Tesla? So scalar field, Tesla field, the measure is not how much it's not and Tesla field is however, giving the complex context for this equation. Typical time is that conformal invariant, so they're excited. They just see flat inverse from their point of view. But if you couple that Tesla field explicitly to the scalar field times energy infinite, and with the feature of, piece of heavy lifting, you can make a Liouville anisotropic. And so now, Liouville stands anisotropic using x direction, defined differently from y and z direction. Now, if it's zero or constant, you can observe this into differential coordinates, so, but you can't do that if data is time dependent. So the question is, how large is this data block over h to make it dimensional? Now, if you have only scalar fields, which do not have any frequent direction, then this data block just decays by 1 over a cubed, and because a is exponentially, it's exponentially correct. But if you had a vector field, for example, you can keep pumping your energy into creating so-called anisotropic stress and surface stress. That's just force. So if you ignore the anisotropic stress here, solution is this. But if you have a force, what makes your anisotropic? And then there's a finisher of it. Basically, your power spectrum is anisotropic. Usually, when we write down the power spectrum, we say it depends only on the magnitude of k, not the direction. But if you able to find this anisotropically, during inflation, it's got this term that depends on the before direction. That's very generic. But if you have a specific model like the one I showed, you can calculate what it is. And basically, you now depend upon number of which is 15 squared here, so which is not perfect. horizontally dominating electromagnetic polarization. So this is what you look for. So therefore, you need to look for specific pattern of sort of D-mode polarization. When you have some polarization direction here, you should see 45 degrees to the vertical, and you should see them harmonic. Not just one. We haven't found it, and for many ground days, the balloon experiments are taking data, and maybe tomorrow that we get an answer that we found. In the meantime, what you're doing is satellite with Japanese party. Jakarta is the Japanese visa, Japanese NASA, from LightBed, and basically we try to do 100 times better than what one satellite could have achieved for measuring location risk, with a few thousand superconducting detectors and things. And when down selected by JAXA, one of the two competing missions for the launch date in 2025. We're not selected yet, but we hope we will be, and then do the thing. So the change of scale ratio, the amplitude of gravitational wave dividing the amplitude of gravitational potential is what we want to find, and current around is less than 0.07. With that, you can try to constrain pressure model, so you have this diagram of the scale ratio in devices, by model 2 and that was what we had in fact 2007. That's the data of publication, so what we showed, here we showed this for just 2006. 3 years, 5 years, 7 years, 9 years, you have okay for this today. And you combine it with ground phase, telescope, you get that, and you combine it with depth distribution, you get that. Okay, cool. So now we are there. Then that red is what we had for our plant result. This is after our plant, so then you see that after our plant didn't change. This model, the rule out, then the result, then it's the rule out. So there's an easy fix to that. If you have no minimal coupling between scalar field and this center, this scalar, we showed it like 9, but you can bring this thing down here. And because if you have this no minimal coupling, your potential, 6 feet lambda 5 to the 4,
with the measuring the polarization and maybe down to the 10 level. So to begin with, I think
reality of living. Is that consideration? Thank you for the question. So if we wanted to do generic longer-term studies, there's also because of the problem. But we have a model that gives us a specific prediction for the shape. So this is just an amplitude, but it might have depending on K1, K2, K3. There are specific tensors for, which wouldn't be the same as problem. In fact, the same is true for scalar mode. And the last figure that whether we ever get to non-related measurements on the locality, we decide. And it will be, the stuff will be more challenging, but I hope that we will do it. Well, here again. Good morning, everyone. It's a great pleasure and honor to give a talk at Stephen's birthday conference, and I'm also the here for giving such a nice introduction to the physics of the cosmic microwave background. And what I want to get into in this talk is the level of complexity that we come to when we try to probe fundamentals of physics with cosmological data, and particularly the cosmic microwave background. We've established the cosmological model as we know today using data from the cosmic microwave background, and in particular the temperature fluctuations. So all of this evidence-based data that has been established comes essentially from the scale fluctuations. Where we need to go next in order to probe the nature of this immunological cosmological model we've established is much more difficult, and it involves trying to do not just cosmology, not just fundamental physics, but what I call mud wrestling. I'm going to show you some of that mud wrestling and show you how the sausage is made essentially. So let me start by saying that some of the work I'm going to present at the start of my talk comes from the hard work of a lot of people. It's the Planck collaboration. Here is some of the Planck collaboration. So it's the work of a lot of people, and especially the students and postdocs that work on this data. So to start with, let's pause again and look at the history of the universe. And so much of what we've learned from cosmic microwave background has come from this time, 380,000 years as the initial time. And if we were to detect gravitational waves, so as it here shows, inflation generates at least two types of waves, density modes and tensor modes. So if we could detect these tensor modes, we could rewind all the way back to the very, very early times, the era of inflation and the end of inflation. So I want to show you, first of all, what we have learned from studying the light from here, and what we could learn if we could actually disentangle all of the foregrounds and lensing and all these effects that we just talked about, rewinding to the very early time. So I'm going to skip through most of the detailed history of the cosmic microwave background and just show you how the data has improved. This is essentially jumps in decades, just showing data from space. It's an incredible set of measurements that's enabled by the technological improvement in detectors and systematic instrumental control of the ability with which we can measure these fluctuations in a sensitive way. And as it here shows, if you have a velocity gradient and a log tracking surface, you're going to generate a temperature quadrupole, and that generates an E-mode polarization pattern. So if you then look at how this pattern is correlated with the hot and cold spots of the cosmic microwave background, you can see that here's the intensity, and here is the polarization, the two slope parameters. So here we're just showing Q of it. So if you have a cold spot, you are going to see a tangential pattern in polarization around it. And in a hot spot, you're going to see a radial pattern around it. So this is stacking the Planck data. This is the theory prediction, and that's the measurement. So it shows you the consistency between temperature and polarization in measuring the cross-correlation between these two modes. And in this kind of really impressionistic granular-like color scheme, what you see is the hot and cold temperature fluctuation. This graph, I believe, has been filtered at quite about 5 degrees, and you might not see this on that, but there's a texture on top of that map, and that shows the preferential direction of vibration. That's basically showing E-modes only there. And if you filter the map at different scales, you're going to see that these fluctuations and these preferential directions of vibration are actually present at all these scales. So this is a 20-octave map. And as the image here shows, there's a way to compress these maps, these 50 million pixels really in the Planck data, exactly into the angular power spectrum. This is assuming that the initial random field is actually Gaussian random field, but as it here shown, we know that that is true to a very, very high degree of confidence. So once you do that, you can compress the data into sufficient statistic and produce an angular power spectrum of the cosmic microwave background. This is an interesting plot. I looked through my notes when I'm stating here working on W map, and this is the first plot of the power spectrum that I could find. And so I call it the first light spectrum. It's the first time we started to fit cosmological models to the data. You can see this interesting discrepancy between the theoretical model and the data. That's because we still had fine-tuning to do analyzing it. So this is a historical example of what the CMB data looks like at the start of the 2000s. This is what it looks like now. This is the Planck 2015 temperature power spectrum. And so the error bar that you can see goes more into cosmic variance. At large scales, it's dominated by cosmic variance. At small scales, it's dominated by noise. What you're seeing there is the picture, the standard lambda deviant model. And here is the temperature polarization cross-correlation. And the red line is still the fit only to the temperature. It predicts this cross-correlation extremely well. And this is the polarization E-mode autocorrelation. And again, this is just fit to the temperature. So there's a lot of consistency in the data, and it allows you to constrain cosmological models. What we're doing here is actually a radical data compression. The quadrillion of measurements of the time stream which gets pushed into the form of mass, the 50 million pixels, you compress that down to 2,500 multipoles, and all of that data is fitted by a cosmological model that just has 6 parameters. There's an amazing degree of simplicity to fit all of this data. But before we start ourselves on our marks, I want to remind you that the cosmological model that we have has what I call 3 tooth fairies. Okay, so first of all, the standard model of particle physics, which we have tested extremely well in the laboratory, does not explain all of this data. We need dark matter, we need dark energy, and we need initial conditions. And all of these things are